So we'll start with nonlinear systems, and when we are talking about nonlinear systems, what we'll be actually dealing with is two groups of systems. You know what linear systems do? Linear systems follow the principle of superposition and homogeneity. So as far as linear systems go, they follow the principle of superposition and homogeneity. Superposition, as you know, if you have an input x1 giving an output y1 and input x2 giving an output y2, so a combination of these two inputs x1 plus x2 will give you an output y1 plus y2. When applied to the same system, if the system follows this principle, then it's actually following the principle of superposition. And if x gives you an output y, then alpha x should give you an output alpha y. So this is what a linear system follows. Now when we'll be talking about nonlinear systems, we'll be talking about a that do not follow uh, the principle of superposition and homogeneity, S and L, fine. Superposition and homogeneity, these systems will not be following the principles of superposition and homogeneity at all. And two, we'll be talking about systems that are not sufficiently linear. So we'll be talking about one group of systems that is not following superposition and homogeneity at all, and two, we'll be talking about a group of systems that is not sufficiently linear. That means they are actually linear in a certain range for a certain period of time, but beyond that range or beyond that period of time, they exhibit non-linear behavior, that they do not follow superposition or homogeneity. Your output and input relation no longer is linear in nature. So we'll be dealing with both types of systems. One that does not follow superposition and homogeneity at all. So these are actually known as uh, hard non-linearities, while as second group of system is they will be linear but they will not be sufficiently linear. That means in some uh, there will be a portion, there will be a range, there will be a period of time in which they will be exhibiting non-linear behavior. And you already know the characteristics of a magnetic saturation. So for example, we are talking about by increasing the field current, flux increases, but to a certain range. After this, what happens is that the system, uh, the flux saturates and does not increase at all. So this is actually a example of a system that is linear over a period of time, over a certain range, but after that range, the flux gets saturated and it does not, and uh, it does not change. Even if you increase the field current, flux will not change. So that type of, it saturates, and that is actually an example of a system that is not sufficiently linear. So जब हम बात करेंगे इस course में, we'll be talking about both these systems, both groups of systems, hard nonlinearities as well as soft nonlinearities. Hard nonlinearities, they do not exhibit at all the linearization and superposition behavior, while as there may be systems that will exhibit linear behavior, but after a certain range, after a certain period of time, they will exhibit a nonlinear behavior. Now, why it is important for us to study nonlinear systems? Uh, so there are a number of reasons why we will be dealing with nonlinear systems, why we need to study nonlinear systems. Uh, the first reason is all physical systems are nonlinear in nature. So when we are talking about real-time behavior of physical systems, so almost all the physical systems, they exhibit a non-linear behavior. This may not be evident as such. This may not be. This we are not talking about. In a certain range, they will be exhibiting linear behavior. Over a certain period of time, they will be exhibiting linear behavior. But over a lifetime, or even if for a short duration of time, there will be systems. All physical systems, they are actually non-linear in nature. They will exhibit non-linear behavior. So it's actually very hard to find a system that will actually behave linearly over an entire life cycle. It's actually very hard to find a linear system. Non-linear systems are uh, easily available and everywhere around you in nature. So all the physical systems being non-linear in nature, so it becomes important for us to study the behavior of non-linear systems. Secondly, to overcome the limitations of linear theory. So classically what we used to do is to since the non-linear uh, control theory was not that developed, linear control theory was very much we had actually been able to understand linear control theory much easily, and it was actually a lot of literature was available. So classically non-linear systems were also studied through linear behavior only. So uh, what we can do is actually we can linearize a non-linear system, apply the linear control theory to that non-linear system, to that linearized model, and understand the behavior of that non-linear system. But the uh, but this there is a limitation to this. So all systems cannot be linearized. One. Secondly, applying linear behavior to nonlinear systems is not going to give us exactly the accurate behavior of the system. What will be the effect of nonlinearities in this system will not be exactly evident to us, as well as while designing certain while linearizing a nonlinear model, we take some assumptions. We uh, we are actually talking about systems behavior in small range of operation wherein it is actually linearizable, fine, but we are not talking about the entire duration of time. So when we are talking about small range of operation within which we will actually base our analysis, so what it will result in is a poor development of a linear controller for such systems. So applying linear control theory to nonlinear systems will have its limitations. A, because of the fact that all the models cannot be linearized accurately. Two, we are taking certain assumptions while linearizing. that actually makes that actually does not give us an exact behavior or exact operation of this nonlinear system, and actually it results in development of poorly fabricated linear controllers for these nonlinear systems. So we need to actually overcome this limitation, and for that nonlinear control theory is gaining actually a lot of uh, focus, and uh, there are new and new controllers being you can see new controllers being identified, and a lot of research is being carried out in this area. Thirdly, uh, dealing with hard nonlinearities. Hard nonlinearities, they are simply those systems that cannot be linearized. Fine. So we'll be looking at different types of nonlinear systems. Hard nonlinearities are those systems, those nonlinear systems that cannot be linearized. So even in a small range of operation, they cannot be linearized. There is because of the mathematics, because of the nonlinear dynamic equation that is governing such systems, it is difficult. It is actually impossible to linearize such systems, and since we cannot linearize such systems, we cannot apply linear control theory to such systems. So previously there was no such mechanism actually to understand the behavior of such systems, to design controllers for such systems. So for that we had to look into nonlinear dynamic equations, had to study the nonlinear dynamic equations, we had to analyze and accordingly design the controller for such systems. So dealing with such systems again, we need to study the nonlinear systems. So there are a number of hard nonlinearities, like you have on-off nonlinearity or relay type nonlinearities. We'll be looking at these different types of nonlinear systems. Yes, so we are talking about why to study nonlinear systems. Uh, we are we are talking about three things. One, all physical systems have nonlinear dynamics. Two, to overcome the limitations of linear control theory and apply to nonlinear systems. Three, dealing with hard nonlinearities, such systems that actually cannot be linearized, how to analyze those systems. For that, we need to develop nonlinear dynamic model of such a system, need to analyze that nonlinear dynamic equation. Fine. So what I am actually talking about is, जैसे हम linear control theory में करते हैं, first of all develop a mathematical model either through transfer function approach or a state space approach. Two, then analyze the system for stability, for controllability, for observability, and then once you have done those things, then you can design a controller, a state feedback controller or a PI controller, any controller that for that linear system. Now similarly we'll be doing in nonlinear domain as well. We'll be first of all defining a nonlinear dynamic equation for such a system. We'll be trying to find ways to analyze these nonlinear dynamic equations. When we talk about nonlinear dynamic analysis of nonlinear dynamic systems, so it is a little bit complicated as far as linear dynamic analysis goes. And then once we have done the analysis, we can then design controller for such nonlinear systems. Fourthly, we need to deal with model uncertainties. Yes. Fourthly, dealing with model uncertainties. So there. So when we talk about model uncertainties, or what happens is, even when we talk about, say for example, a linear system, uh, parameters change. Linear parameters change with respect to time, with respect to the environment, with respect to temperature, with respect to different conditions under which they are operating. So the system parameters are subject to change, and since these system parameters change with respect to as time goes on, the system behavior does not remain constant, and the linear controller is not actually designed to to fit into this model parameter variations in the system. So for checking the parameter variations in the system, we need to design nonlinear controllers like adaptive controllers or robust controllers that are actually nonlinear controls, and where uncertainties in system model parameters are also taken care of. Fine. So so different parameters of a system are subject to change with respect to time, with respect to the environment, and these parameter variations need to be taken into consideration while designing a system, while designing a controller for a system. Linear control theory does not deal with model parameter variations, but nonlinear controllers, they are suited, they are designed to keep into check the model parameter variations as well. So again, this is another reason why we need to understand the behavior of a nonlinear dynamic equation and not just a linear dynamic equation, even for a linear system. Say for example, you have designed a transfer function model or a state space model for a DC motor. So while designing that transfer function model, while designing that state space model, you may have encountered the parameters like armature resistance, armature inductance. So these resistance, these inductances, they change. Resistance changes with temperature. So as the motor keeps on running, the temperature of the system increases, the armature resistance changes. So your transfer function model or state space model is no longer valid for that as the temperature increases. Similarly, your armature inductance, your leakage inductance will change with saturation. So these parameter variations need to be taken into consideration while designing a system, and that a nonlinear control is able to do much better as compared to a linear control system. So you have model reference adaptive controllers in a that are actually based upon nonlinear dynamic equations, and you can design those for certain systems to keep into check the machine parameter variations. Fifthly, for simpler design. So for nonlinear systems, when we are linearizing the system, then taking into consideration various assumptions, then designing a linear control, it becomes actually a complicated process, and this design is actually little complex. While as if we directly apply a nonlinear, directly analyze a nonlinear dynamic equation and design a controller for it, it becomes a simpler task to do. Fine. Sixthly, as is with every system, cost and performance. So with analysis of nonlinear systems in the nonlinear domain, uh, we can actually optimize the cost as well as performance of the system. So these were actually points why we are studying nonlinear system, because of the because every physical system is nonlinear in nature to overcome the limitations of linear theory, dealing with hard nonlinearities, dealing with model uncertainties, that is system parameter variations, fifthly with simpler design, and sixth, optimal cost and performance design of such systems. Uh, Now we come to the behavior or the properties of nonlinear systems. So there are a number of properties, a number of characteristics of a nonlinear system that you have not studied in case of linear systems. Fine. A nonlinear system does not follow superposition and homogeneity. So that's actually the main property of linear systems. It follows superposition and homogeneity principle. So nonlinear system does not do that. So that thing is not valid here. Second, first rather, multiple equilibrium points. So what's an equilibrium point? You have studied the state space model of a system x dot equal to x plus bu. So equilibrium point is a point where x dot is equal to 0. That means the system dynamics, x dot means dx by dt. So where the system dynamics stop to change, at what point of time, at what point they stop to, the system states become constant, they do not change anymore. So that point actually represents the equilibrium point. Now in case of linear systems, there is a unique equilibrium point. So you can only find out a unique equilibrium point from the state space model of a system. You simply put x dot equal to 0 and you will get that point. But with nonlinear systems, there will be a number of equilibrium points. There will not be one equilibrium point, there will be a number of equilibrium points. There can be one, there can be two, three, number of equilibrium points in case of a nonlinear systems. Now why these nonlinear equilibrium points are important? Because we'll be actually dealing with stability. So when we actually analyze stability, we analyze the stability of a system around the equilibrium point. So this is true for linear systems, this is true for nonlinear systems. That means in case of linear systems, when there is only one equilibrium point, so if you analyze the system stability there, you will say that either stability will be, either the system will be stable, it will be unstable, or it can be marginally stable. Since there is only one equilibrium point, so that is it. But with nonlinear systems, since you have number of equilibrium points, so at each equilibrium point you are finding out the system stability. So there may be equilibrium points where this nonlinear system will be stable, there may be equilibrium points where the nonlinear system will be unstable. So there may be certain points, certain equilibrium points where the nonlinear system will be marginally stable. So there is no defined stability of a nonlinear system. So you cannot simply say that this system, this nonlinear system is stable or unstable or marginally stable. So that is a second point with regard to the properties of nonlinear system. So stability of nonlinear systems is not defined. You cannot straight away say that this nonlinear system is stable or unstable or marginally stable, because each and every equilibrium point will have its defined stability or instability or marginally stability. While as for a linear system, you can straight away say that this linear system is either stable or unstable or marginally stable. That is not true for nonlinear systems, because with number of equilibrium points, the stability will also be defined differently for each and every equilibrium point. So accordingly, this equilibrium points will now you'll say this equilibrium point is stable or unstable, this equilibrium point is stable or unstable. So that is how it goes with respect to nonlinear systems. You define the stability of an equilibrium point, you do not define the stability of the system as a whole. So that's 1 and 2. 3, frequency response.
So please repeat the last point.
In case of nonlinear systems, as I said to you, the first property is there are number of equilibrium points. We have not studied the nonlinear dynamic equation yet, so इसलिए मैंने वो अभी दिखाया नहीं. But simply an equilibrium point is where your system dynamics stop to change. That means where x dot becomes equal to 0. So with respect to linear systems, this is one point. So linear systems में एक ही equilibrium point होगा, but non-linear systems में multiple equilibrium points आएंगे. ठीक है, they can be within the that state space plane. There will be a number of points that will actually be corresponding, that will be actually equilibrium points of this non-linear system, where your system dynamics will be x dot will be equal to 0. And as far as stability goes, we define stability at the equilibrium point. So since the linear system has only one equilibrium point, so we can say that this linear system is stable or unstable, because इसमें तो एक ही equilibrium point है. But as far as non-linear system goes, there are number of equilibrium points. So you will say that for a non-linear system, you will say this equilibrium point is stable or unstable. this equilibrium point is stable or unstable. You cannot as a whole say that this non-linear system is stable or unstable. उसके लिए फिर आपको सारे equilibrium points को पहले analyze करना पड़ेगा. अगर सारे equilibrium points stable है, then only you can say that this non-linear system has all stable equilibrium points. So stability of a non-linear system is not fixed, like you can say it is stable or unstable. Stability of non-linear system will depend upon stability of each and every equilibrium point. So you need to find out equilibrium points for that. Equilibrium point is simply a point in that state space plane where x dot becomes equal to 0, where your dynamics stop to change. Is this clear? We'll go into the details. We'll be understanding how to find out equilibrium points. We'll be understanding how to find out stability of systems, how to find out stability of equilibrium points. I'm just highlighting the properties right now. Am I audible to everyone? Is my voice breaking?
Yes, sir.
ये सबको इश्यू हो रहा है?
यस सर, बहुत ब्रेक हो रहा है.
Anyways, I'm also recording this meeting, so ये इसके बाद YouTube पे अवेलेबल होगा, मैं उसके लिंक भी शेयर कर लूँगा. So you have multiple equilibrium points, you have stability of nonlinear systems. Thirdly, frequency response. Frequency response behavior. So for a nonlinear system, when you apply for a linear system, when you apply a sinusoidal input, this is a linear system, you are applying a sinusoidal input of a certain magnitude, certain frequency. So what you can expect is your output will have the same frequency. It can be shifted, it can be phase shifted, fine, वो तो हो सकता है लीनियर सिस्टम्स में, बट फ्रीक्वेंसी वही होगी जो आपके इनपुट की थी. ठीक है. सो लीनियर सिस्टम्स में द इनपुट एंड आउटपुट हैव द सेम फ्रीक्वेंसी. If input has a frequency of sine of omega t, your output will also be having a frequency of omega t, fine. But as far as non-linear system goes, if you apply a sinusoidal input, there are a number of possibilities. You can have a behavior where your output is, firstly, it is not necessary that your output will be sinusoidal in nature. It can be any shape, any way, right? And secondly, even if it is sinusoidal in nature, it will have a different frequency as compared to that of the linear system. ठीक है. ये आपने actually if you have studied these things already in power electronics in a lot of detail, harmonics. तो आपके नॉन लीनियर सिस्टम की वजह से हार्मोनिक्स इंट्रोड्यूस हो जाते हैं सिस्टम, जिसकी वजह से आपका जो आउटपुट बिहेवियर होगा, इट कैन बी एग्जिबिटिंग एनी हार्मोनिक फ्रीक्वेंसी कंपोनेंट. ठीक है. फर्स्ट हार्मोनिक, सेकंड, थर्ड, फिफ्थ, एनीवे. सो हार्मोनिक्स इज ऑल्सो अ कैरेक्टरिस्टिक प्रॉपर्टी ऑफ अ नॉन लीनियर सिस्टम, जिसकी वजह से आपकी जो फ्रीक्वेंसी ऑफ द आउटपुट है वो भी चेंज हो जाती है. ठीक है. सो यू ऑलरेडी नो अबाउट हार्मोनिक्स इन द सिस्टम. फिफ्थली, jump resonance. Okay. Limit cycle is actually important property of non-linear systems. That you have chaos and you have bifurcation. Fine. So there are a number of properties of non-linear systems. I'm just highlighting these properties. I'm just listing these properties. You have multiple equilibrium points. Equilibrium points कैसे निकालते हैं, उनका analysis कैसे करते हैं, that we have to do in detail. Then stability of non-linear systems, again that will be covered in detail. Frequency response, इतना कुछ ज़्यादा है नहीं. लीनियर सिस्टम्स में क्या होता है कि आपका जो इनपुट है और आउटपुट की जो फ्रीक्वेंसी है दे मैच. But in case of nonlinear systems, your input and output frequency may or may not match. Fine. Your output may not be sinusoidal even for a sinusoidal input. That does not happen with a linear system. Fourthly, you have the property of harmonics. So harmonics में आपको पता ही है कि nonlinear system की वजह से क्या होता है कि your output will be actually be composed of a number of waveforms that will be having frequencies that are multiples of your fundamental frequency component. ठीक है. So we have covered this extensively in your power electronic course, in your power systems course. Then you have jump resonance. Jump resonance क्या होता है? Yeah, you already know what is resonance. So there is a point where your system behavior peaks and जैसे आपको पता ही है for an RLC circuit, as XL becomes equal to XC, your system is totally resistive in nature. So this is a point where resonance occurs. Fine. So with any nonlinear system, what happens is now if this is a case of a linear system, आपने इनपुट को इंक्रीज किया, आपका जो आउटपुट है वो इंक्रीज हो रहा है या वट एवर दिस इज. At certain point it will obtain a peak and then decrease. If you reverse the input, what happens is it will retrace the path. But what happens with case of nonlinear systems is if you have a peak at one point while tracing one path, अगर आप back जाओगे, if you reverse the input, what will happen is you might have a peak somewhere else. ठीक है. So there will be so with nonlinear systems, what happens is as you increase the input, the output increases. There will be a peak, then the output will again decrease with respect to the input. But if you retrace the input, if you decrease the input in linear systems, the same path is retraced. But in non-linear systems, the same path is not retraced. You might obtain a peak somewhere else. So this is actually jump resonance. तो ये आपको actually अगर if you also remember hysteresis में भी यही होता है. If you increase the input, BH को अगर आपको याद होगी तो जैसे आप B को इंक्रीज करते हैं H इंक्रीज होता है. But then if you decrease B, H decreases, but it does not retrace the same path because of the alignment of the magnetic domains. So this is a similar phenomenon. Hysteresis is actually a type of non-linear system. So यहाँ पे भी वही हो रहा है. इनपुट को आपने इंक्रीज किया, आपके आउटपुट में रेजोनेंस आ गया. जब आपने रिट्रेस किया पाथ, you may find out a peak at some other point as compared to when you were traversing the forward path. In the reverse direction, you may obtain a peak somewhere else. So there can be a number of jump resonances. There can be a number of points where you may obtain peak with respect to non-linear system. This is called jump resonance. Then limit cycle. Limit cycle is one of the most important properties of a non-linear system, and this will again be studying in detail. What is limit cycle? Limit cycle is a non-linear system basically exhibits this property, that is, it shows an output behavior of fixed amplitude and frequency without any external disturbance. Fine. So there can be this is not necessary it will be of this shape only, but limit cycle क्या है? आपका जो non-linear system है, without any external disturbance, its output will be exhibiting an oscillatory behavior of fixed amplitude and frequency. Fine. This is an oscillatory behavior. of fixed amplitude and fixed frequency and without any external disturbance. So if you take an example of a Van der Pulse oscillator, so उसमें आप देख सकते हो कि आउटपुट ऑसिलेट कर रहा होता है without any external disturbance, and this behavior is actually known as limit cycle. We'll be discussing limit cycle in detail because it's one of the most important properties of nonlinear systems. Then there is the property of chaos. So what is chaos? In case of linear systems, initial condition does जैसे कि हमने ट्रांसफर फंक्शन में भी देखा है, initial condition does not define the stability of a system. Even if we talk about state space models, initial condition does not change the stability of a system. Initial condition has no role in defining the stability of a linear system. But in case of nonlinear systems, initial condition plays a very important role in defining the stability of a system. So एक initial condition पे आपका system stable हो सकता है, दूसरी initial condition पे आपका system unstable हो सकता है. So this is a property that is exhibited by nonlinear systems. So by changing the initial condition, how your output response basically behaves, and if there may be a and if it may go totally into unstability, that's actually referred to as chaos. Fine. Again, we may not be discussing chaos in much detail, but we'll be looking at the impact of initial conditions in a nonlinear system. Initial condition का क्या impact होता है? We'll analyze that using the nonlinear dynamic equations that we'll be studying. So these are different properties: multiple equilibrium points, stability of nonlinear systems, frequency response of a system, how the frequency response of a nonlinear system is different from that of a linear system, the property of harmonics, the property of jump resonance, the property of limit cycle, the property of chaos, and bifurcation. Bifurcation is basically when we talk about parameter variation. So parameter variations का क्या effect होगा output पे, that is actually the property of a bifurcation. As I have discussed with you, machine के जो parameters हैं, they may also define whether your system is stable or unstable. In linear systems, the machine parameter variations do not disturb the stability of a system, but in case of nonlinear systems, the machine parameter variations will disturb the stability of a system, will change the output or nature of the system. So that is the property of bifurcation. So these are some of the properties of linear systems that are actually different from that of, these are the properties of nonlinear systems that are actually different from linear dynamic linear control, and these are the properties that we'll be discussing while studying the nonlinear systems. Okay? So we have to discuss some of these properties in detail. Some of these properties we may not be discussing in much depth. Some of them we may not be even discussing at all from here onwards. Fine. So that's all about the properties of nonlinear systems and why we study nonlinear systems. So that's all.